our final cleanup of our ideas in section 2.2. Today we're going to look at a little bit of the theory that establishes for us our existence and uniqueness of an initial value for the solution of the initial value problem for the second order constant coefficient homogeneous ODE with the two initial conditions, one on the function at some point and one on its derivative at the same point, right? That's as easy as it gets. We're going to generalize all of this to non-constant coefficients, right? So this is constant coefficient. So A, B, and C, as you know, are what? Good. Real numbers, right? And since it's second order, A can't be 0, right? So these guys are constants. We're going to, from here, generalize this idea to non-constant coefficients, what we can say about solutions, although it's not easy to find them anymore if it's not constant. And we're also going to generalize to higher order, so not just second order, third, fourth, fifth, sixth, nth order. That's where we're going to go from here. But first, before we do that, we want to look at a little more of the theory within existence of a unique solution to the initial value problem. Okay, so let's start with this guy because it's the easiest case we could possibly do. The theory is a little more complicated for a non-constant coefficient, and we'll just state some theorems when we do that. Okay, so let's think about it. So suppose, right? Suppose that's a capital S, which means suppose. I guess I'll write it out. Suppose that we claim that y is equal to c1 y1 of x plus c2 y2 of x is the general solution. This is running out. Nice black marker, nice thick. It's running out. Okay. It's the general solution to the ODE. So what have we been doing? We've got a nice second order ODE that's homogeneous, and what did we say? If we could find two solutions, y1 and y2, right? Two functions that individually satisfied this equation and show that one wasn't a multiple of the other, that they were linearly independent, that we could claim that those guys were a fundamental solution set for this differential equation, and therefore all solutions could be represented in terms of them. These two solutions span the solution set because all we need to do is create a linear combination. These words are words you're going to hear later some more. A linear combination of those two solutions, and that produces every possible solution. Okay? All right. So then what if we want to try to satisfy the initial value problem, right? So to try to satisfy the IVP, right? Well, we're going to need to know what y prime is because we have to plug into there, right? We need y prime, so let's write that one down. So this guy, this is y as a function of x, right? So just to be more explicit, all possible solutions are a linear combination of these two special ones that we found that for constant coefficient are relatively easy to find, right? Regardless of which case we're in, right? That's what all those other videos were about. So to try to satisfy the initial value problem, we need to know y prime, okay? So we need to know y prime, because you got to know y prime of x in general first before you can plug in a value, right? So what is y prime of x? How do I take the derivative of this, right? So y prime of x would be to take the derivative of the entire thing, right? c1 y1 plus c2 y2. We'll do this out one more time just to be clear about what's happening. That would mean take the derivative of that whole thing. But we've got these awesome rules from calculus, right? That the derivative of a sum is the sum of the derivatives, yeah? And so that would say that sum rule would say it's okay to say that, right? The derivative of this sum is the sum of those two derivatives, but each one of those individual derivatives is the derivative of a constant times a function, right? And what is the derivative of a constant times a function? What rule is that? Good, the constant multiple rule, right? When a function is multiplied by a constant, yeah? The constant multiple rule says the derivative of a constant times a function is the constant times the derivative of the function, right? So we're going to use that constant multiple rule twice. Derivative of c2 y2 of x is c2 times y2 prime at x, right? So here is y prime of x, yeah, and there's y of x, right? Okay, so now we have to try to satisfy the initial conditions, okay? So therefore, what do the ICs say? Well, what is y evaluated at x naught? Well, I put an x naught everywhere I had an x, right? So y at x naught is c1 times y1 evaluated at x naught plus c2 times y2 evaluated at x naught, right? And I'm going to ignore what I want them to be for right now. Right now I'm just going to evaluate. So what is y prime evaluated at x naught? Well, y prime evaluated at x naught just means I put an x naught everywhere I see an x down here, right? Yeah, just evaluate that. So you guys tell me, what is it? I'm listening. Good. Keep going. Keep going. Keep going. What? Very nice. Y prime at x naught is c1 times y1 prime evaluated at x naught plus c2 times y2 prime evaluated at x naught, right? Okay? So, what do the ICs require? The ICs then require, well, we want what? We want y at x naught to be equal to alpha, right? So now to make my life simpler, I'm just gonna erase stuff, right? So the ICs imply, well, maybe I'll do that in blue just to, so in order to consider the ICs, we need these two things. And so what do the ICs imply? What do we want? This is what y evaluated at x naught. What do we want y evaluated at x naught to be? We want it to be alpha. And what is alpha? Some given real number, right? Alpha and beta are given. Alpha and beta are real. Yeah? Okay. All right, and then what about y? This is what y prime at x naught is. What do we want y prime of x naught to be by the initial conditions? We want that to be beta. Yeah? Okay, so these two guys are known, right? y1 and y2 are known, so evaluating y1 and y2 at a particular value, x naught, are known. If we know y, then we take y prime, and then we can evaluate y1 prime and y2 prime at some particular value, x naught, and then that becomes some known number, right? Okay, known numbers. And so this is really, what is this? This is a system of two equations for two unknowns. Just like an algebra system, what are our two unknowns? Yeah, our two unknowns are C1 and C2, right? C1 and C2. Those are the unknowns, right? Well, there's two unknowns and there's two equations, so that's pretty good, right? But just because there's two equations for two unknowns doesn't mean you're going to have a solution, right? Okay? So, I will let you go ahead and work out the algebra, because that's going to be no fun to watch. And also in an attempt to at least make one of these videos short, right? So I'll let you work out the algebra, however you would do it. Solve one equation for C1, plug into the other equation, so, solve for C2, multiply, or whatever it is that you do, multiply one equation by something, nice and useful. Same with the other equation, subtract. You do it however you want. You should be able to show this, okay? So, solve for yourselves. to show the following. To show that C1 can be written as alpha y2 prime evaluated at x naught minus beta y2 evaluated at x naught, all divided by, making sure I'll write one, y1 at x naught, y2 prime at x naught, minus y2 at x naught, y1 prime at x naught. That's what C1 can be solved for. Remember, each one of those things appearing over there is just some number that's known, right? And C2, and this is not something to memorize. We just want to write it down, show that we can solve for these guys. So again, whatever your favorite technique from high school algebra of solving for two equations and two unknowns, it's just now that there's letters there instead of numbers. You've got to understand what letters are just known numbers. C2 is beta y1 of x naught minus alpha y1 prime evaluated at x naught, all divided by y1 at x naught, y2 prime at x naught, minus y2 at x naught, y1 prime at x naught. Okay? So you should be able to solve that and come up with, solve that system over there, two equations, two unknowns, come up with that. Whoa, what do you see? What do you see when you look at that? What do you see? What's our goal? We want to know, right? In order to satisfy the two initial conditions, we have to be able to solve this system for unique values of these constants, right? So for the IVP, right, for the IVP to have a unique solution, right, which is always our goal with initial value problems, right, to have a unique solution, we need to be able to pick out unique values of C1 and C2. There has to be only one and only one value of C1 and C2 individually that would satisfy this system of equations, right? So for the initial value problem to have a unique solution that exists, right, that's kind of in there, that idea is in there, that exists, right? We must be able to solve the system for unique values, C1 and C2, so there should be only one solution for C1 and C2. We have a formula, right, that we have demonstrated, so that's good, right? There's only one solution there. Coming from our algebra, since these are just numbers, real numbers, we must be able to solve the system for unique values C1 and C2 that exist, right? They have to exist. That's the rub, right? When would they maybe not exist? Yeah? You seeing it? You seeing it? Okay. So, our C1 and C2, which we demonstrated right here, right, will be unique, and they are unique, and they'll exist provided what is true. Yeah. Right? The denominator can't be 0, right? Back to the same olds, right? The denominator can't be 0, right? With division by 0, it's not going to get us nice real numbers, right? So our C1 and C2 exist provided, and now I'm just going to erase just to make my life simpler, right? Here we go. Here it goes, right? Okay. It's the same denominator, right? y1 at x naught times y2 prime at x naught minus y2 at x naught times y1 prime at x naught. Same denominator. That's super cool, right? Okay. Provided this quantity right here is not because if that quantity is not 0, then those C1 and C2 will exist. Yeah? Well, that's a weird thing. So this quantity arises naturally. Right? For C1 and C2 to exist. Right? We cannot divide by 0. Well, that's kind of cool. Totally random, maybe? Or is it? Well, this arises naturally for C1 and C2 to exist. What was the whole point of C1 and C2 to exist? Well, that was so that we could actually satisfy these two initial conditions, and the ability to satisfy the two initial conditions from our general solution means that, okay, well then we would have the general solution, and we'd be able to solve this guy uniquely for any constants alpha and beta, right? One and only one solution for the initial value problem, right? So this quantity arises naturally for C1, C2 to exist, right? I.e. for there to exist a unique solution to the initial value problem. So maybe it's not so random. Maybe it actually is a kind of an important quantity that keeps coming up over and over again, so then we give it a name, because that's usually what happens when something keeps coming up over and over again, and it is sort of important, right? So we give it a name. We call it the Wronskian of y1 and y2. Oops. The Wronskian of y1 and y2 evaluated at, you tell me, where is it evaluated at? Good, x0. That's a lot of words. The Wronskian of y1 and y2 evaluated at x0. Well, what do we do when we have some quantity that comes up all the time and that we like? And so we give it a name, but the name is long, so we invent some symbols that mean that, right? Here we go. What are the symbols that mean that, right? We're going to define this to be the Wronskian, capital W, of y1, or sometimes people use a lowercase w, y1 and y2, the Wronskian of y1 and y2, evaluated at x equals x0, okay? Or just evaluated at x0, we could do it like that, okay? Yeah, that's totally fine too, okay? Means evaluated at x, or whatever your independent variable is, at x0 is equal to x0, right? That's the Wronskian. So if the Wronskian is non-zero, then we'll have a unique solution to our initial value problem, right? Okay, well that's kind of cool. Let's see other ways we could write this. Let's explore this thing a little bit more. This isn't really in your book. They mention it and say it doesn't, really arise naturally, but it does. Anyway, and it's gonna be an important concept of linear algebra, linear independence that we're gonna wanna be able to refer to. So we're gonna generalize this a little bit later as well. So it's just good to be aware of it. Okay, so what's another way to think of this guy? So we could write it like, the Wronskian of y1 and y2, right? Evaluated at x0. Instead of putting the of x0 into each guy, we could say, right, y1, it's even just to be shorter, instead of saying y1 of x times y2 prime of x, we could say y1 times y2 prime minus y2 times y1 prime, all evaluated at x0, right? Okay? You'll even see this written like it's a function, so evaluated at x naught. The Wronskian of y1, same thing. The Wronskian of y1 and y2 evaluated at x naught. Okay? Okay? So this might be simpler, right? Just because it's less writing. This weird little quantity, what is it? Like, it's mixed products, right? So it makes you think a little bit like of the product rule, right? The first function times the derivative of the second function, the second function times the derivative of the first function, but there's a minus in between, right? Okay? So it makes you think a little bit about that. So it's a mix and match of function times derivative of the one function times the derivative of the other, minus the reverse, right? So it's kind of a little bit hard to remember which goes which, like, the quotient rule, right? If you guys didn't have your song, it'd be crazy trouble, right? But it matters, right? Like with quotient rule, because it's a minus, yes? Okay. So what to do? It might be nice then if we had some other way of like remembering it instead of having to just remember which piece goes first, okay? So you can't go wrong with always starting with y1. That's all super simple, right? Start with y1. If you start with y1 and you know you got to multiply by the derivative of the other guy, well then you know it's y1, y2 prime. And for the Wronskian, we know it's a minus, right? And then we know what comes after is the reverse, right? This guy, the function, times this guy, the derivative, yeah? Okay, so that's another way to think of it. So it all comes down to whether or not that quantity evaluated at the place that we're assigning the initial condition is not zero. If that quantity is not zero, then we have a unique solution because our C1 and C2 exist. So that's pretty cool. It's pretty obvious. On the other hand, if that quantity is zero, right? I probably shouldn't have erased the guys that came before, but remember our formulas for C1 and C2, this was in the denominator. So if this quantity is zero, well then, your C1 and C2, they aren't gonna exist, right, okay? So you're either gonna have no solution to our differential equation, or no solution to satisfy the initial conditions, or maybe only one of them will exist, and you'll be able to have, like, get rid of one equation and just have another equation, but then there'd be infinitely many solutions, because there'd be one equation with two unknowns, C1 and C2. And so, in order to get a unique solution, this guy can't be zero. If the guy is zero, you're not going to have that, okay? All right, well, let's think about other ways that we could possibly express this quantity, okay? So, a simpler way to think about the Wronskian, or to remember the Wronskian, this Wronskian. A simpler way to remember this Wronskian, that little change in wording is going to matter later, okay? A simpler way to remember this Wronskian is by using matrices and the determinant of a matrix. Now, if you don't know what that is right now, don't worry about it. We're going to talk about it later. But for now, all you need to know is this. So the Wronskian of y1 and y2 evaluated at x naught is equal to the determinant, so big long lines like this with, for a matrix means determinant, and what is going to go in here? y1, y2, the function across the top, and the second row is their derivatives, y1 prime, y2 prime, okay? So that's the shortest way to write it, so is with the 2 by 2 determinant. 2 by 2 determinant. Another way to write that is the determinant of the matrix, which is a 2 by 2 matrix, y1, y2. We're foreshadowing some things we're going to be talking about later, y2 prime, okay? The determinant of that matrix. And what is the determinant of a 2 by 2 matrix? Okay, so that's the question. Well, maybe you can guess it just by looking at what that is equivalent to. Or whoops, we need to say evaluated at x naught, right? So evaluated at x naught. Okay, evaluated at x naught. Okay, so maybe you can guess what is the determinant of a 2 by 2 matrix. If that expression is the same as that expression, then what happened, right? Well, I took this guy and multiplied times this guy, y1 times y2 prime. That's called the main diagonal, okay, the forward diagonal. From the 1, 1, this is the 1, 1 component, row 1, column 1. This is row 1, column 2, right? Row 2, column 1, and row 2, column 2. So this is the 2, 1 component, and that's the 2, 2 component, yeah? And so we multiply the guys on the main diagonal together, and then we subtract multiplying the guys on the back diagonal together, right? Okay? And so the determinant of a matrix A, B, C, D, 2 by 2 matrix, again, we're going to talk more about this later, is, you guys tell me, yeah, multiply these two guys together, A times D, then subtract, good, B times C. Yes? Okay? All right? Okay. So that makes it easier to remember because it's visual. What goes across the top here is just our guys, our y1 and y2, our two solutions that we're claiming are fundamental solution set. And then this is just their individual derivatives, and then we do the determinant, and that gives us this guy. Okay? And that was necessary for us to be able to solve for our constants C1 and C2, right? So let's look at another view of this idea. Let's recall, what did we need about our y1 and y2? We needed them to be linearly independent. So recall, and I'm not so sure that the green works very well visually to be able to see, so I'm just going to switch to black. This black isn't working well either. Maybe. We needed y1 and y2 to be linearly independent in order to have a fundamental solution set. For the ODE, and then write our general solution as a linear combination of those, right? Okay? C1y1 plus C2y2. So for this, what does that mean? Y1 and y2 are linearly independent. Well, that means C1 y1 plus C2 y2 equals 0 has only the solution C1 equals C2 equals 0, right? Right? So we needed these to be linearly independent on minus infinity to infinity, and this equation has to hold for all x, right? For all x. Real. Yeah? And so what did we do to be able to show linear independence, right? Well, we had lots of different ways. They all seemed a little bit like we were, you know, like pushing symbols around. You could solve and try to plug in values of x and come up with equations and then end up showing that C1 and C2 have to be 0, right? So let's look at another equation that would have to hold, right? So if this equation has to hold for all x, okay, and that's our linear independence, that's the definition, right, for us, right? That's this, yeah? Well, if this equation holds for all x, what if we took the derivative of that equation? Let's take the derivative, okay? Of both sides. What you do to one side, you gotta do the other. Take the derivative of both sides. Can't see that, derivative. Right? take the derivative of both sides. y1 and y2 are functions of x. c1 and c2 are constants, right? So what's the derivative? c1 y1 prime plus c2 y2 prime is equal to 0. Derivative of 0 is 0, right? Yeah? So if this equation holds, then this equation has to hold, right? Yeah? Make sense? Yeah? Totally legit? Okay? So now we have two equations and two unknowns, right? But now, instead of like alpha and beta, right, any arbitrary real numbers, we have zeros on the right-hand side. This is called a homogeneous system, or a linear system of algebraic equations. Well, you know, be a little bit careful. So this is still homogeneous because we've got zeros on the right-hand side. The other one was non-homogeneous with the alpha and beta because they didn't have to be zero, okay? Systems of equations, linear systems of equations and differential equations are intimately connected. We're going there as well. Anyway, we now have these two equations, yeah? Okay? These two equations. And so if we have solutions, a unique solution of these equations, we know, right, clearly C1 equals C2 solves both equals C1 equals C2 equals 0 solves these two equations, right? Okay? Because it's homogeneous, right? It's definitely a solution, right? Okay? And provided that Wronskian is non-zero at an x naught, then that will be the only solution, right? And if that's the only solution, then that comes back up here and says, hey, wait, y1 and y2 are linearly independent. And so lo and behold, we see this connection of linear independence and the Wronskian, right? Okay? And this will be the only solution. If the Wronskian of y1 and y2 evaluated at x naught is not 0, right? Okay? And so that Wronskian non-zero is going to come right back into the idea of the two functions are linearly independent. And so that is super, super nice. So let me see if I can close this up here for us. In the next few minutes. So what do we know? So if our, we'll just try to close it up here. So if the Wronskian, right, I'll say y1 and y2, I'll just say w, just so I don't have to keep writing that, right? You know what I mean, right? So if the Wronskian is not 0 at some x naught, okay? If the Wronskian is non-zero at x naught, then what do we know? Well, back to here, right? y1 and y2 are linearly independent. Well, that gives us another way to check for linear independence. It's a little more systematic, maybe, than some of the things we have been doing. But what we have been doing is perfectly legit as well, right? But it's always nice to have something more systematic, especially when you're going to generalize. That's a hint for things coming up. Okay, so let's talk about what that tells us about the Wronskian. So what is the contrapositive of this statement? Contrapositive, right? Okay, so if I have a statement, if A then B, that's a direct statement. The contrapositive is if not B, then not A. Okay? These are equivalent. They say the exact same thing. They're logically equivalent. Okay? The thing that comes after the then and if switch, and you negate them. So you guys tell me, what does the contrapositive say we can also guarantee? What does it mean for y1 and y2 to not be linearly independent? if y1 and y2 are not linearly independent, so they're linearly dependent, yeah? Then what? Then the Wronskian is going to be 0. Okay? What does it not tell us? So those two things are truths, right? If the Wronskian is 0, we know nothing. Okay? That would be the converse of this statement, and the converse isn't true. Okay? If the Wronskian is 0, then you know nothing about whether y1 and y2 are linearly independent or linearly dependent. They could be either. They could be either. Okay? Okay? So Wronskian non-zero, super happy, linear independence. Yeah? Wronskian 0, then you gotta use a different method to determine linear independence or linear dependence, like the other methods that we've been doing, right? Okay? There's going to be a very special truth about functions that solve linear ODEs, like the ones that we had back here, and well, in the ones that we've been looking at for second order constant coefficient. It's going to be a very special truth about the Wronskian for those types of functions. But that special truth yet to come about the Wronskian for functions that are solutions of linear ODEs. Okay, that special truth is yet to come. Stay tuned. More videos or more class time, one or the other. Let's make this, let's do a couple of Wronskian calculations for some functions that we've already dealt with as solutions in some of our examples to some linear ODEs. Maybe you can guess what the special truth is. That would be fun. Okay? Maybe you can guess. So let's just look at the Wronskian for some of our examples. Some of our examples. Some of our example ODE solutions. Okay? All right. At one point, we had a solution where y1 was 1 and y2 was e to the negative 9x. We showed that those two things were linearly independent in a different way by looking at videos. You can go back and if you forget how. Now let's look at the Wronskian. We would look at the determinant. What goes up here? 1 e to the negative 9x, right? And then what's the derivative of 1? Good. 0. What's the derivative of e to the negative 9x? Minus 9 e to the minus 9x, right? What would this determinant be? Okay. Main product of the two main diagonal guys is negative 9 e to the negative 9x, right? Minus what? 0 times that is 0. So what do we get? Negative 9 e to the negative 9x. Yeah? Okay? What do we know about this? Well, this guy is always positive. This guy is always negative. So negative times positive, right, is strictly negative, right? So what did we care about? We cared about it not being 0 somewhere at some x naught. It's not 0 anywhere, right? It's always negative. Okay. I'll let you do this one for yourselves. You can do the Wronskian e to the 2x, e to the 4x. That was one we had, right? Let's look at this one. The Wronskian of e to the r1x, e to the r2x, right? Okay, where r1 does not equal r2, right? Case 1 of our constant coefficient, right? What do we have? E to the r1x on top, e to the r2x. This guy's just a special case, right? What's down here? What's the derivative of e to the r1x? Good. r1 e to the r1x. What's the derivative of e to the r2x? r2 e to the r2x. Yeah? If we're going to do that determinant, what are we going to get? That guy times that guy, you're going to get an r2 e to the r1x e to the r2x. Yes? Minus this guy, product, r1 e to the r1x e to the r2x. Yeah? What can we do? We can factor an e to the r1x e to the r2x out. And what are we left with? r2 minus r1. Yeah? What do we know about this and this? Strictly positive. E to stuff is always positive. What do we know about r2 minus r1? Well, if we're in case 1, r1 is not equal to r2. So what can you tell me about r2 minus r1? It's not 0, right? This guy is not 0, and so we can say this Wronskian is not 0 ever. Yeah. Right? Let's look at one more. Here were two functions. That we looked at before. We looked at determining whether or not these guys were linearly independent. If we jump to the Wronskian always to determine whether something is linearly independent, right, then what would we compute here? We'd be like, oh, okay, well, let's see, e to the x and e to the x plus 2. And then what? So I should be careful here. I shouldn't. I guess we never did make any conclusion. So, not 0, therefore 1 and e to the negative 9x are linearly independent, right? Okay, so not 0, therefore e to the r1x and e to the r2x are linearly independent when r1 is not equal to r2, right? Okay, now back to our last example here. Okay, what's the derivative of e to the x? Good, e to the x. What's the derivative of e to the x plus 2? Good, e to the x plus 2, right? Derivative of e to the stuff is e to the stuff times derivative of the stuff. This derivative of that stuff is just 1, yeah? All right, what do we get? Determinant, we would get e to the x times e to the x plus 2, right? And then we would subtract, yeah? E to the x times e to the x plus 2. What do we get out of that? Good. 0. What can we conclude? Careful, what can we conclude? Nothing. We can conclude nothing. Right? That's what this says. If the Wronskian is 0, you know nothing. You got to go back to some other method to figure out whether you're linearly independent or linearly dependent. If two functions are linearly dependent, their Wronskian will be 0. But if the Wronskian is 0, it could be either linear independence or linear dependence. So that's one reason not to always just jump to the Wronskian, because in this case, you gotta find some other method. Find another method to use. Well, thankfully, you know one, because we showed these two guys are linearly dependent in a previous example. But showing their Wronskian is 0 tells you nothing. You cannot conclude, right? You cannot conclude e to the x and e to the x plus 2 are linearly dependent from this. Right? Does that make sense? Alrighty, that's that for today, and we will be moving to higher dimensions from here.